G'day, I am Vibrometer from the Center of Asset Integrity Management at the University of Pretoria. The purpose of this video is to serve as training for students to use the Polytec scanning laser vibrometer system that we have in our laboratory. Now just a quick overview of what the system does and what its uses are. In the scanning unit over here you have a helium neon laser source. This light is shined onto your target, and as the target vibrates, the light that is reflected back is frequency modulated by means of the Doppler technique that you observe quite readily acoustically when you hear a vehicle driving past you when you're standing still. Now the system also has got two mirrors that allows us to steer the laser beam, and it makes this system very useful in terms of performing automated mobile testing on structures, especially if I've got many points to measure. Now basically what the system comprises of, as I've already talked about the scanning head. Down here we've got the box that's really got the brain and the electronics. We have a normal Windows PC down here. Our system currently has got Windows XP on it. Here we have a vibrometer controller, and that gives us the output signals from the laser vibrometer. And over here the junction box where we can connect the various signals for recording onto the PC system. Okay, now just a brief overview of our experimental setup. Here I have our scanning laser vibrometer head that we have adjusted to the correct optimal standoff distance. We have our test structure, and we have our excitation source. In this instance we're going to use a speaker to excite the structure in a non-contact fashion. Normally when you do testing like this, you would use an electrodynamic actuator that you connect with a stinger to your structure, but depending on what your need and your application is, a non-contact technique might be more useful. So basically, if you look at the connection of this system over here, now we would connect this, as I said, our vibrometer controller has got analog outputs. We can measure velocity and displacement directly with the laser. The displacement measurement just works slightly different on a phase-based approach as opposed to a frequency-based approach with the velocity. So what we first want to do is connect the output of the laser vibrometer velocity signal up to this input over here, the analog input, labeled Velo. And perhaps I should just mention, with this system, the license we have, we can only use displacement for very, very small amplitudes. So that's more tailored towards acoustic emission measurement for the specific system. So if we get the other licenses, we can measure larger displacements, and with our Polytec PSV400, the oldest system, we can measure up to 15mm displacement, but with this system we cannot. Also our system, although there are 4 connectors here, we only have 2 input channels. So the one is used by the laser vibrometer, and we also have an input for a reference sensor. Now, because we're going to do automated scanning, what makes the system very useful is that it's got a built-in signal generator, and the generator output is here from signal 1, and this generator output we will feed to the amplifier that drives the speaker, and we will also use it as our reference sensor. If you used electrodynamic actuator with a force transducer, you would again supply the signal to the amplifier driving the electrodynamic actuator, but your input signal here will be the signal from your force transducer. So because we want to send it to 2 different locations, I'm just going to use a BNCT connector over here, and we're going to first connect it to the reference input, and then we also connect it at the same time to the amplifier. Now what is very useful also is because we're using the generator of the system, the signal generator, we can trigger from the software, or the software generates a trigger that we can use to for averaging purposes. Now when everything is connected, we can then switch on our controller. Okay, so now everything is connected and switch on the scanning system side. So now we can open the shutter in front of the scanning head, and you will see the laser beam now projected onto our target surface.
Okay, so now we have connected our hardware and we set up our scanning head correctly, so now we can start the acquisition. And to do this, we are going to launch the PSV 8.8 acquisition software. Alright, so this is the screen that you see as soon as we start the software package. You can see a number of bars, but I'll just go through them as one would sequentially. So the first is the optics bar with a blue bar indicator showing us a signal level. Ideally we want this bar as high as possible, but generally as long as we can see a blue bar and the amplitude is relatively stable, we should get good results. We can also perform autofocus of the laser beam. So you can just demonstrate that here. If you click autofocus, the software will adjust the focus until it obtains a maximum signal level from the laser beam. So you can immediately see how that signal level increased from the previous levels. The generator, we're not going to worry about that, as well as the position. Very important though is here at the status indicator, the Z level is our standoff distance, which we have set to 0.711 meters, and this will give us the X and Y locations of the measurement points we're going to generate in a while. Down below is a control bar for the camera. So with this we can control the zoom of the camera, as well as the focus of the camera. We can also click this button, the autofocus button, that automatically focuses the camera in the scanning head. So we're just going to adjust the zoom until the test object fills the screen, and just press the autofocus button again. Great. Now the next step is to perform alignment of the laser beam. Now this is important to get correlation between where the laser beam is and the points that we are going to define in a while. So if you see, if I drag the laser beam with by clicking the left mouse button, you can see that there is almost no correlation between the laser position and the cursor location, and that is what we need to correct. So to do this, we're going to click on the Perform 2D Alignment button. You'll typically see alignment points that were created in the previous measurement, so we'll just right click and select delete all, and then with the middle mouse button we drag the laser beam to a location on a flat reference surface, which in this case will be our hub. Click it to a location, drag it to a location with the middle mouse button, and click on it with the left mouse button. Typically you need not more than 5 points, but you'll just have to evaluate that for your specific setup. So when we're done with that, we just click on that button again, and now we can see if we drag the laser beam with the left mouse button, it follows the cursor quite well. A very important point to note is if there are major offsets in the test object in terms of standoff distances, this alignment will not hold. So for example, if you look at the wall, on the wall at the back, that distance or that alignment is not very good, but generally for 2D measurements it's not a major problem. Okay, so now that we've performed the alignment, we can now define our scan points, and we start this by clicking on this button over here. As you can see over here we have several templates which we can use to create points. We can create points in a line, a rectangle, an ellipse, or a polygon. Just to demonstrate some of the functionality of these templates, say we want a rectangular pattern, we can decide whether we want points generated only on the edges of the shape, points only within the edges of the shape, and both points within the edges and on the edges. We also have control over the pattern of the grid, namely rectangular, polar, triangular, or random. Furthermore, we can also adjust the point density. We can increase it or decrease it. We can even rotate the grid pattern if we need to. Another option is to create discrete points, which you do by clicking on this button over here, where you can move the laser beam to a specific point and create a point at the location of the laser beam. So we can just create points by clicking, and we can connect them as necessary. But for this exercise or demonstration, we're not going to look at that just now, so I'm just going to delete that. We're going back to the template environment. So if we use the templates that are presented here, you can use a rectangular pattern to define points in our blades, and in this case I want points both on the shape edges and within the shape. Rectangular grid pattern is sufficient, and the density is also quite appropriate. Now what is nice is we can simply copy and paste this pattern by using Ctrl C and Ctrl V, and then rotate the grid shape, do it for the remaining number of blades. Great. So the next step is to define scan points on our hub, and we'll use the elliptical shape for that. And of course, in this instance, we'd rather make use of a polar pattern, and we can decrease the radial and angular density. We can also decrease the vertex points. Let's make this 10. And of course, you can see it generated a point here in the middle, which we do not want. So we can remove that by drawing another ellipse and just subtracting that ellipse from the ellipse below it, and that removes that point. Now, because we're exciting the structure with a speaker cone, I would just like to measure some points on the speaker cone itself, just to make sure that the results are not distorted by the dynamics, if any, from the speaker cone. So I'm just going to define a couple of points, just a rectangle, points on the edges. Now, of course, I can go and create discrete points, or a discrete point, but then you lose some functionality in terms of the geometric shapes that we've defined. Okay, so our next step now is just to make sure that all our points are indeed on our structure, and we can do this by clicking the left mouse button and dragging the laser point to the specific locations, and everything seems fine. This pattern over here we can perhaps move. We'll do that just now. We see over here there's some discrepancy, so we need to adjust that as well. And also we need to make sure that these points are indeed on the speaker cone, which they are, but you can see in the background there's a reflective strip that I installed, so I would like the points to be on that. So let's just quickly adjust all that. So you can simply click on the shape and move it with the cursors. We wanted to move this shape also. And now all our points are nice in shape. So it's quite an important step, just to make sure that all our points are indeed on our target. Now, also what you probably already noticed is that there is not a very good alignment between the points I've defined on the speaker cone and the location of the laser. The reason for this is simply that we performed alignment using the hub flat surface as our reference, and of course the speaker cone is about 15 centimeters behind that, and that's the reason for this misalignment. But for this exercise, we're only interested to get an idea of the dynamics of the cone, so we're not too worried about the alignment in this case. But it did, as you noticed, it did make it a bit more difficult to find the scan points that the laser are at the location that we need it to be. Okay, so now that we've checked that the laser locations are where we need it to be, we also need to check the signal strength at the different locations. We can see on the hub the signal strength is quite good, but on the blades not so good. Now typically when we measure with a laser beam, with a laser vibrometer, optical reflectivity is very important. On the one hand, you don't want a very shiny surface, because that will act as a mirror and deflect the laser beam, and you won't get sufficient light reflected back into the scanning head. On the other hand, a matte surface is more appropriate, and fortunately our test object here has got a matte finish from the manufacturing process that was used. If your target does need surface treatment, you can install optoreflective material or paint the structure with a matte paint, or use something that we call developer spray, which is like a white powder that you spray onto the surface. Now, what we can also do is adjust the focus of the laser beam at that point. So let's see what happens when we do this for this location over here. and we can see that we do get an increase in signal level. However, it affected obviously the focus on the hub over here. So a nice feature of the software is that we can assign individual focus parameters to each point, and we do this by pressing Ctrl A to select all the points. We right click, select modify selected points, and we can either assign a focus automatically or manually. For us it will be easier to do this automatically, and the software will now go to every point and perform an optimization exercise to optimize the signal strength. So let's give the software some time to do this. Okay, so now the software has completed assigning focus values, and we can see we're getting much better signal strength at the various points. That point struggling still a bit. So one option to increase signal strength at a specific point would be to add or treat the surface there optically. But let's continue. So the next step is to go to the acquisition settings, and the good idea is to start simply from left to right in terms of the tab. So the first tab, we can select whether we want to record FFTs, our range of frequencies, fast scan, where you capture data only at around a certain frequency, and typically you would also excite at that specific frequency. And also if you want to perform a time measurement, generally FFT is a very good option and is used quite often. Averaging, very important if you want to get rid of noise and just get better results. I would suggest using the complex option so that you store phase information as well. Number of averages, the minimum is 3, and you can go as high as possible, but you just need to be aware that the more averages you define, the longer it will take to perform the scan. So just be aware of that. Remeasure is important. If the software is not happy with the signal strength at the specific point, it will increase the number of averages for that specific point until it gets better results. We can select automatically adapt the vibrometer range for points with overrange, so it's basically an auto range, but I'm not going to choose that just now. Then our input channels, first we select the measurement direction, and I'm going to happy with the +Z direction. The measurement range of the digital to analog, from the data acquisition system. Let's make it 500 millivolts. The quantity for channel 1 is velocity. We can also select displacement if our vibrometer is set up that way, but for this purpose we're using velocity. The sensitivity, that's adjusted automatically by the software, and I'll show you this later. Reference will be voltage because we're using the signal generated by the system as our reference, but we have a whole range of options: sound pressure, angular velocity, etc. But just to show you, if we had a force transducer as our reference, we will select that, and then we can enter the sensitivity of the sensor over here. Let's just take that back to voltage, adjust it to 500 millivolts. Filters we can use, so the vibrometer generally we start with no filtering and adjust as necessary, but you can see you can define low pass, high pass, band pass, and notch filters. The next step is to define our measurement bandwidth. So This is shown in megahertz, so the bandwidth over here is 1 kilohertz. But for our system, we can go up to 40 megahertz, but that would again, you just need to be aware of what you need to get out of the test. But let's keep that at 1 kilohertz. And we can see on the right hand side that it shows us a sample frequency 2.56 kilohertz, sample time and frequency resolution. Now that we can adjust by defining the number of FFT lines. We can create or select a high number of FFT points where you get very fine frequency resolution, but you will see for each measurement the sample time is now quite long, over 100 seconds. So again, just be aware of what you select. So I'm going to select 1600 FFT lines, giving me a sample time of 1.6 seconds and 0.625 Hertz resolution. Next, windowing, which is quite important, specifically if you either use an external signal generator or if you have a random signal, you would typically select handing window or hamming, etc. force if you are using impulse excitation. But again, because we're using the generator of the system and the system is then triggered by itself, so synchronization is not an issue, we can use the rectangular option, and of course we're also going to generate a signal that is going to keep on repeating. So if we did generate a purely random signal, even with the system, we would have had to select a window, but we're going to generate a repetitive signal. Triggering, very important, so we can either select off. So this is something you'd select if you either use random excitation or if you simply wanted to measure a time series. You can also select analog if you have an external signal. You can use a vibrometer to trigger itself. I would definitely wouldn't recommend that, but reference if you have a reference input signal. In our case, because we're using the signal generator of the system, and because we've connected it in the hardware as we showed earlier, we can select the external or TTL signal, which is ideal, and we can select rising or falling edge, etc. Next is Speckle tracking or signal enhancement, and that again is just if the laser at the specific point is not giving a very good signal to noise ratio, this option will allow the software to slightly adjust the laser location until a better signal to noise ratio is obtained. Best will mean it will take longer and search longer for better signal to noise ratio, but we're just going to select fast. Over here with the vibrometer, we can select different decoders, the measurement ranges. We can go from 1 millimeter per second up to 1 meter per second measurement, but for now let's keep it at 5 millimeter per second. Over here is what you would select for the displacement decoder. Again, for the PSV400 we only have the one option. On the PSV300 system we've got a wider range available. Tracking filter is quite useful if you have signal dropout, and typically would make that fast or slow, but you do need to check your measurements. Sometimes it's better to switch it to off, but let's keep it at fast. Low pass filtering you can again perform, also high pass filtering, which doesn't give us much options, so we'll just keep that at off. Next, our signal generator, and here we can either create sine waveform exciting only at a single frequency, a periodic chirp, or a sine sweep. Set a random signal, so it will generate a random signal, but then play that same random signal over and over again. burst chirp, you can see burst random, white noise purely random, sweep, that's for a longer sine sweep time, and so forth. User defined is quite useful if you need to generate a signal in an external program such as MATLAB and then import it, but we are going to use periodic chirp, and here you can adjust the amplitude. So for the amplifier that we're going to use to drive the speaker, the maximum peak to peak input voltage is 300 millivolts, so 0.15 is the absolute maximum we can adjust it to. Offset is not important over here. Okay, so now that we've set that up, we now need to check that everything is in order. So to do this, we will switch on the signal generator, and we increase the amplitude on the amplifier so that we get sufficient excitation levels, and then we can select continuous measurement. So that's just to check measurements. It brings up this window over here showing us the response. So I'm just styling the windows. Over here you can select what to display, vibrometer or reference. So this is our generated signal and our measured signal, and we are observing low frequency activity, which is simply because the speaker or the test object is suspended from bungee cords. And let's look at the speaker, and we see this sitting with over range there, so we do need to adjust the measurement. So currently we're displaying the vibrometer output in millivolts. We can also select it to display velocity, but voltage is great for defining the input ranges. So let's just quickly adjust that. So we go to channels, so let's increase that to 2 volts. Let's see, still too much. Make it 5 volts. 10 volts. Okay, so we see that the signal is still too high, the amplitude. So what we'll do is go to settings and change our vibrometer sensitivity. Instead of 5 mm per second per volt, let's make that 10 mm per second per volt, and that's much better. Just looking at the blade tips, but that's not a problem. Great. So everything seems fine. The tracking filter seems to be working correctly. So let's switch off the generator. I'm going to do it by clicking that button over there. Stop the continuous measurement. Okay, so now we're ready to perform our scan, and to do that you'll click this button over here, the scan button, and I would definitely recommend first switching off the generator, because the advantage of doing it like that is when the software starts the scanning, it will automatically switch on the generator and switch off the generator when the scanning is done. So that is useful specifically if your test is going to take a while to complete. So I now have an option here to rename my or define my file name. Let's call it bladed disk scan. We can enter information such as project name, the user, and also comments if we need to. And as soon as we're going to click save, you can hear the software switching on the generator, and the scanning commences. What we are observing is every now and then there seems to be a signal dropout or some transient event for that specific point. Averaging managed to remove that, but if we find that it doesn't, then we just need to go and adjust the measurement, and my first suspect would be the tracking filter, and that we will need to play around with. But while that is carrying on, something to take notice of is this window over here. Firstly, it shows us how many measurement points we have defined in our software, which is 187. The blue points shows us the location is not measured yet, which is 97.9% of the defined points. Optimal, which is what we do want, this gray, and we can see the points that it has already measured. So 2.7% of the points have been found to have optimal signal strength, and it also shows us an estimated remaining time left, which is quite useful. If you sit with an overrange at a specific measurement, it will make the specific location yellow, and unfortunately then for that specific point measurements won't be available. So that's why it's very important to make sure that your vibrometer sensitivity is set correctly. So let's leave that to complete and see what our results look like. Okay, so our scan completed in just under 54 minutes, and it took longer than the initial estimated time because the software remeasured several points. After the scan, we got a screen that showed that all the points on the disk at optimal status, which is wonderful. So now that the scan is complete, we can go to the presentation mode to have a look at the results, and we press the presentation mode button. Now when we go directly from the scan to the presentation mode, it does ask us to automatically open the previous scan, which I already have done. So on this screen we see the RMS values of our overall measurement, and we can see that the speaker cone dominates the measurements. So that also means that our spectral results showed over here, and this is the average spectrum of all the scan points, is going to be dominated by the speaker points. So I think first let's select all the speaker points and invalidate them for now, and we do this by selecting the points, right clicking and say modify selected points and invalidate. See, we have to do them one by one. Invalidate, 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 and you can see how the spectrum changes. And now that we've invalidated those points, we can get a better idea what the structure itself is doing. So what this means, we are discarding the dynamics of the speaker cone just to analyze the results, and if we do find any suspect motion in the results, we can validate those points again and see what the speaker is doing. Okay, so let's go to define frequency bands, and this allows us to select the peak frequencies in a structure to look at the operational deflection shapes, and we can select the item to display, so it will be vibration, velocity, that's fine. We can select the scale as decibels, and then we simply draw peaks or bands around the peaks of interest. So let's select that peak there. There we can increase the window. Peaks over there, there. And when we're done, you can click select or calculate peaks, close this window, say yes. And if we press the play button, we can see what the structure does at the different frequencies. So we see the first bending mode, or the first umbrella mode of the structure at 171 Hertz. Another mode, again probably effects from the speaker cone. Speaker cone effects. At 707 Hertz about, we start seeing torsional vibration of the blades. 782, start seeing second bending mode of the blades. Increase, and 821 Hertz, we see a very nice mode of the blades. Now you can see that it perhaps was not such a great idea to define the scan points on the speaker cone, although it did help us to determine which of the peak frequencies were due to the speaker cone and which were due to structural modes of scanning or of the structure. A better approach would have been to use another laser vibrometer to measure the dynamics of the speaker cone and use that as our reference. So that in hindsight would have been a better approach. But yes, there we have our several operational deflection shapes. Okay, so that was great for visualizing very quickly our results. Now, if you want to use these measurements to perform a proper modal analysis, we need to export the data. And to do that, we go to File, Export, Universal File is what I would recommend. It automatically asks or suggests a file name based on the file name you use for the scan. We just say save, and you can see there's a whole lot of options we can select. We can export just the results from the selected bands. We can export the data of the points, and again a lot of information available here. You can select everything, but your file is going to be very big, so I would suggest only selecting what you really need. So typically we want FFTs of the vibration, and velocity is the measurement or the direct output from the system, so I want to use that. So if you use the force transducer or some other reference signal, you can also export the transfer functions, H1 or H2 estimator, and coherence. You can also export the display objects, in other words the XYZ coordinates of the points, and you can see the object distance here, which we defined prior to performing our scan. So if you happen to forget to define this before performing the scan, you can adjust this now. My general suggestion would be to export a universal file for every parameter, and compatibility with something like Model 2, the star compatibility works quite nicely. You can also define a reference point, so that is the location of your reference transducer if you used one. So if we performed, or if we're interested in FRF measurements, I would simply go and select H1 velocity over voltage and coherence, and export that as an output file. And to do this, we simply press OK, and then we can import our data into an external program such as Model 2 or MATLAB or whatever you need. So this concludes this training video. You are welcome to contact the lab personnel if you require any further information. Thank you.